Okay, let's talk about concentration units. Concentration units are very important, and so there you can have mass concentrations, so mass concentrations are usually denoted by C, and these could be milligram per meter cubed, these could be microgram per meter cubed, so concentration is mass over volume. So in mass concentration we have mass over volume, so which is mass of pollutant over volume of air. As an example, carbon monoxide standard is 10 milligram per meter cubed. So these are mass concentrations. Then we also have volumetric concentrations. And these are also called mixing ratios sometimes. And we're going to be using these very extensively throughout the course, so make sure you understand all of these. So mass concentrations are denoted by C, and the volumetric concentrations are denoted by Y. And these are measured as a percent of parts per million, parts per billion, and so forth. So here the numerator is, say, the volume of pollutant divided by the volume of air. Also it's moles. You could also alternatively say it's moles of pollutant divided by the moles of air. Now again, taking the example of carbon monoxide, the CO standard in volumetric concentrations is 9 ppm. Which is actually, if you parts per million, so could say that is 9 into 10 to the power minus 6 parts of or meter cubes of carbon monoxide per meter cube of air. Or we could say 9 to 10 to the power minus 6 moles of CO over for every mole of air. Okay, let's take an example. So these examples you can access on the in-class example sheet, which is posted in the week 1 module of Canvas, and each week these will be posted and we will be solving these examples. So let's take this example. So here I'll suggest you pause the video and read the example and try it out on your own before you look at the solution. So if we solve this, so ping pong ball has a certain mass and a certain volume, is inserted in a bottle, and that bottle has a certain mass and a certain volume. So let's see, if we consider, say this is our bottle, and this bottle is about 200 gram. Maybe there is some water in it, I don't know, let's just assume that. And then you inserted in that bottle the ping pong ball. So that's a ping pong ball now. And now this is 200 gram, and actually the ping pong ball weighs 0.5 grams, so the weight would slightly increase. Now don't ask me how they got the ping pong ball through that narrow neck. Probably the neck is wider than the ball. Okay, so here what's given to us, we know the mass of bottle is 200 grams. We know the mass of ball is 0.5 gram. We know the volume of bottle is 100 mils, and the volume of the ball is, the volume of the bottle is 1 liter or 1000 mils. It's 1 liter, and the volume of the ball is 100 mils. Which is, you can also say, is 0.1 liter. So now let's look at the three parts of this problem. Part A, we have to estimate the concentration of the ball inside the bottle in terms of mass over volume, grams per liter. So this is C, mass over volume. So this would be simply mass of ball over volume total. So this is 0.5 grams. This will remain 1 liter. So the answer would be 0.5 grams per liter. And I always recommend students to box their final answer. That's helpful to identify what you solved for. Okay, second one is in the volumetric units. Volume over volume. So that's Y. So that would be V ball over V total, and that's 0.1 liter divided by 1 liter. That's 0.1, which we know is equal to 10%. And the last one is in terms of mass percentage, that's X. So that would be mass of ball divided by M total. So that's 0.5 grams divided by 200 plus 0.5 grams, And if you solve for this, it will be something around 0.0025, and this ratio would be 0.25%, and we are calculating in percent because that's what the problem asks us to do that. Okay, let's look at example 2. Again, I encourage you to pause the video and read the example and or the question and try to attempt to solve it on your own. Okay, so here we are given that on a polluted summer day in Fairbanks, the ambient ozone concentration is 70 ppb, and we have to convert this concentration ppm. So we will, it's a relatively simple problem that I will try to approach it in two different ways. So method 1, we have 70 ppb. So now let's consider this, that 1 ppm is 10 to the minus 6, 1 ppb, parts per billion, is 10 to the minus 9, and if you divide these two equations, then what does that mean? So 1 ppm divided by 1 ppb is 10 to the power 3. So we can say that 1 ppm is 1000 ppb. So if we use this here, that 1 ppm is 1000 ppb, so that gives me that this is 0.070 ppm, right? So we basically use some of these relationships and apply them here. Okay, now let's do another method. It's just a way of looking at it. So we have again 70 ppb, and now let's consider that, say, 10 to the power 6 ppm is actually 1 and a value of 1, and that's 10 to the power 9 ppb is also a value of 1, and just in that line of thought, 100% is also considered 1. So if we use this relationship, so we multiply and divide by 1, so 10 to the power 6 ppm divided by 10 to the power 9 ppb, and that would give us the same answer again. And it should, right? There's no reason it should not. So this is again doing the same thing. It's just the way of thinking. There's two ways of thinking about it. Okay, for part B now, we have to convert 21% oxygen to ppm. So 21% O2 is equal to, let's use, say, method 2. So 21%, we multiply and divide by 1, So 10 to the power 6 ppm divided by 100%. They're both 1, we know from here. And so what does that give you? About 210,000 ppm. Okay, so with that we will move on to the next topic, which is we want to learn how to convert between C and Y. So say if you're given C in the units of gram per meter cube and we want to find Y in the units of, say, meter cube per meter cube, how do we do that? So how do we do that? Well, one way you can look at it is the denominator is the same in both cases. What we need to do is to change the numerator. So we convert the numerator from gram of pollutant to moles of pollutant, and from mole we can convert it to meter cube. How do you convert from grams to moles? So recall some of your chemistry, and to convert from grams to moles we need to divide by the molecular weight. We get the moles, and once we have the moles we just multiply by volume over mole. Okay, so now where do we get the volume over mole? So now we need to go back to more of chemistry and remember the ideal gas law. PV is equal to nRT. So this just a quick refresher on this. Here P is pressure. P stands for pressure, and in the units of atmospheres or pascals. P naught is considered the atmospheric pressure, which is 1 atmosphere, and which is also equal to, in terms of Pascal, 101,325 pascals. V is volume. Could be in meter cube, could be in liters. N is number of moles. And R is the ideal gas constant. And some of the values used for R are 8.314 pascals meter cube per mole Kelvin, or more commonly we will be using 82.05 into 10 to the power minus 6 meter cube atmosphere per mole Kelvin. and also 0.0821 liter atmosphere per mole Kelvin. So these are different values of R that are used, and then T, temperature, by now you have figured out it's in absolute values. So absolute temperature is measured in Kelvin, and temperature in Kelvin is just 273 added to temperature in Celsius. So okay, so now we're going to use this. So how are we going to use this? So we need, here we need V volume over mole, right? We need V over N, or let's say we need volume over mole, right? So V over N would be equal to P over RT from ideal gas law, or sorry, V over N would be RT over P. Confused myself there. And now what for standard conditions? So this is a term that you might see, standard conditions. So what are standard conditions? Standard conditions are that temperature is 25 degrees Celsius and pressure is 1 atmospheres. So for these standard conditions, then here the T would be actually 273 plus 25 would be 298 Kelvin. Right, so V over N would be RT over P, and if we substitute 82.05 into 10 to the power minus 6 meter cubes atmosphere per mole Kelvin. I always like to write the units and work them out. So R times T over P. P is 1 atmospheres. And if we see how these things cancel out, atmospheres cancel with atmospheres and Kelvin cancels with Kelvin. So this boils down to V over N is equal to, if you solve for it, I encourage you to punch these numbers in your calculator and solve for these, 0.0245 meter cube per mole, or 24.5 liters per mole. We can also invert this, so N over V would be 40.9 moles per meter cube. So these are at standard conditions, and something to kind of make a note of these standard conditions, because if you're given standard conditions, it becomes very easy to convert. Okay, so to summarize now, if you want to convert from your concentration in grams per meter cubed, you convert first to moles per meter cubed, and from there you convert to Y, and here we divide by molecular weight, here we multiply by V over N. So one could say that Y is equal to C over mW, its molecular weight, times V over N, and we have shown that V over N is RT over P, and so we can, so this is kind of our formula here, so we want to box this. But then if we have a specific case for standard conditions, as we discussed, for standard conditions only, it would be Y would be equal to C over mW times 0.0245 meter cubes per mole. And in these formulas we know that C is mass concentration, right? It could be milligram per meter cubed, it could be microgram per meter cubed, and the molecular weight is, or MW is molecular weight, which is in the units of mass, say grams per mole, and Y is the volumetric concentration, which is meter cube per meter cube or mole per mole. Okay, let's look at this example. The CU standard is given as 10 milligram per meter cube. We have to express this in the units of ppm, so converting from C to Y. We are also given the molecular weight of CO, and it seems that we are being indicated that these are standard conditions. So let's see what's given to us. We are given the molecular weight. The molecular weight of carbon monoxide is 28 grams per mole, and we have to convert 10 milligram per meter cube to ppm at standard conditions. And how do I know it's standard conditions? Because it's temperature of 25 degrees Celsius and a pressure of 1 atmospheres. So let's recall our formula that we just learned. Y is equal to C over mW, and since this is standard conditions, I can write 0.0245 meter cube per mole. So okay, let's substitute all of these in here. So the concentration is, and make sure you write all the units because it's very vital, very important, else you can have mistakes. And the molecular weight, let's also convert this to the grams to milligrams, so it would be 28,000 milligrams per mole. Just making my life a little bit easier by getting these in the same units. And if you're wondering how I got these, I can do that on the side here a little bit. The molecular weight of CO is 28 gram per mole, and we know a gram has 1000 milligrams. So this cancels, and this gives me 28,000 milligrams per mole. So that's on the side. Okay, let's... Okay. So coming back to our main problem here. So now if you plug this all and into your calculators and calculate this, so we get about 8.75 into 10 to the power minus 6. It would be, which is equal to actually 8.75 ppm. Now you might be wondering how I got this. So this is, I can do that a bit slower. So that's what we had, 8.75 into 10 to the power minus 6. Now recall that 10 to the power 6 ppm is equal to 1, right? So I can multiply this by 1, right? And so multiply it by 1, which is 10 to the power 6 ppm, I just said. So these cancel out, and I can say this is 8.75 ppm. So just so that you can understand that better. Okay, so that's our answer right there. Let's do another problem, another example, example 4. So in this case, we have to do the opposite. We are given a concentration of ozone in Fairbanks on a hot summer day is 80 parts per billion, and we need to convert this to the units of milligram per meter cubed. So let's quickly jot down what we are given. We are given that ozone concentration is 80 ppb parts per billion, and then we have to find what is the value in milligram per meter cubed. And it says assume the pressure is 97% of the sea level pressure. Well, the sea level pressure is actually 1 atmospheres. So we can say the pressure here is 0.97 into 1 atmospheres is 0.97 atmospheres. And now our formula that we were using was, so far we used y equal to c over mw times RT over P. So if I want to calculate C, then that will be y times mw times P over RT, right? So now let's see, we want to calculate C. So we substitute each of these things. We are given 80 parts per billion. Okay, let's do it slowly, and I will write everything with all the units. 80 pp, oops, 80 ppb, so that could be 80 into 10 to the power minus 9 and times the molecular weight, which is now for ozone is the molecular weight for ozone is 16 times 3, which is 48 grams per mole, times P over RT. P we just said is 0.97 atmospheres, divided by R. If we plug in the value of R, 82.05 into 10 power minus 6 meter cube atmospheres per mole Kelvin, and the temperature is 273 plus 35 would be 308 Kelvin. So okay, now let's see what all is cancelling out. So atmospheres cancel with atmospheres, Kelvin with Kelvin, and this mole would cancel with mole. So we are left with gram per meter cubed, which is what we want. And if you plug all of these values into your calculator, which I highly encourage you do, you would get a concentration value of 1.47 into 10 power minus 4 gram per meter cubed. And I want to get it in milligrams, so I know 1000 milligrams make a gram. So this is 0.147 milligram per meter cubed, or I could say 0.15, just rounding it off. All right, so that's how we would convert volumetric concentration to mass-based concentration.